Tonight, we will consider a reality that seldom enters our thoughts. When astronomers refer to the observable universe, they are describing a cosmic volume that measures about 93 billion light-years in diameter. But there is a profound subtlety in this definition that invites a moment of reflection. The simple fact that we call this vast expanse observable does not mean we have actually observed it. In truth, we have not come anywhere close. This exploration will reveal the sheer magnitude of what we have yet to see and clarify why the great majority of the cosmos remains hidden from our view. On a clear night, far from the glow of city illumination, one might wonder how many stars are visible in the sky. Under the most pristine conditions, a person with perfect vision can discern approximately 9,000 distinct stars across the entire celestial sphere. Our own galaxy, the Milky Way, is estimated to contain between 100 billion and 400 billion stars. This means that the unaided human eye perceives roughly 0.00002% of the stars within our home galaxy alone. Now, let us expand this perspective. The observable universe is thought to hold around 2 trillion galaxies, with each one containing billions, or in some cases, trillions of stars. The total stellar population has been calculated to be in the vicinity of 200 billion trillion. And yet, with our own eyes, we can perceive just 9,000 of them. This simple comparison begins to frame the immense scale of our subject. The picture becomes even more intriguing when we focus specifically on galaxies. While individual stars are far too numerous to ever count directly, galaxies represent the fundamental structures of the cosmos. They are the great cities of stars, the primary building blocks of the universe's architecture. And it is here that the numbers reveal a surprising truth. We know that approximately 2 trillion galaxies exist based on meticulous observations and sophisticated mathematical projections. However, the number of galaxies that have been observed in any detail is far smaller. As of 2025, the most extensive galaxy surveys have managed to catalogue somewhere between 10 million and 50 million galaxies. If we take the more generous figure of 50 million, that still only represents about 0.0025% of the total. To put it another way, for every single galaxy we have studied in detail, there are about 40,000 more that we have not yet examined. If the universe were a library containing 1 million books, our current progress would be equivalent to having read just 25 of them, from which we are attempting to comprehend the entire collection's story. One might naturally ask why this enormous discrepancy exists, especially with our powerful modern telescopes and centuries of astronomical study. The explanation is a confluence of several challenging factors: time, technology, and the overwhelming scale of the undertaking. First, consider the sheer size of the sky. The complete celestial sphere spans about 41,000 square degrees. Our most powerful instruments, like the Hubble or James Webb Space Telescopes, do not view the entire sky at once. Instead, they focus on incredibly small patches of it. The renowned Hubble Ultra Deep Field, for example, reveals about 10,000 galaxies within a tiny sliver of the sky that covers only about 1/13 millionth of the total area. If the entire night sky were the size of the United States, the Hubble Ultra Deep Field would be comparable to the size of a tennis court. Capturing that single, iconic image required hundreds of hours of dedicated exposure time by the Hubble telescope. This illustrates the core problem. To see the faint, distant galaxies, an instrument must stare at a single spot for an extended period. But the sky is vast, composed of millions of such patches, and we can only observe them one by one. Second, there is the critical distinction between different types of observation, particularly regarding technology and resolution. Not all astronomical data is of equal value. It is one thing to detect a galaxy, which means identifying a faint smudge of light in an image and confirming its presence. It is quite another to observe it in detail. A simple detection might confirm a galaxy's existence and its approximate location, but to truly understand it, to determine its distance, chemical composition, age, and internal structure, requires a technique called spectroscopy. This process involves splitting the galaxy's light into its constituent wavelengths and analyzing the resulting patterns. Spectroscopy is exceptionally time-consuming. The Sloan Digital Sky Survey, a project that ran for many years and created one of the most detailed galactic maps to date, successfully obtained spectra for about 2 million galaxies. While 2 million is an impressive number on its own, it pales in comparison to the 2 trillion galaxies that exist. This amounts to just 0.0001%, or 1/10,000th of 1% of all galaxies having been analysed spectroscopically. The vast majority of what we count as observed galaxies are merely photometric detections. These are based on broad imaging where we can confirm that something is there, perhaps estimating its brightness and apparent colour, but lacking any deeper information. An analogy may be helpful here. Imagine trying to understand every city on Earth. Photometric detection is like flying over a city at night and seeing its lights. You know a city exists below, and you can make a rough guess at its size based on the extent of the illumination, but you have no knowledge of its architecture, the language spoken by its inhabitants, its culture, or its economy. To gain that knowledge, you would need to land, explore the streets, speak with the people, and study the place intimately. That deeper level of analysis is what spectroscopy provides. And we have only performed these detailed ground visits for the equivalent of 2 million cities out of a total of 2 trillion. The rest remain just distant lights seen from an airplane. Third, there is the challenge posed by distance and faintness. The universe is in a state of constant expansion. As light travels across cosmic distances, it gets stretched, a phenomenon known as redshift. The farther away a galaxy is, the more its light is shifted toward longer, redder wavelengths. For the most distant galaxies, their light has been redshifted so profoundly that it moves entirely into the infrared part of the spectrum, rendering them completely invisible to optical telescopes. Seeing them requires specialized infrared instruments, such as the James Webb Space Telescope. Even with such technology, the light from these remote objects is incredibly faint, often reduced to a mere handful of photons by the time it reaches us. Detecting these faint signals demands extremely long exposure times and instruments of extraordinary sensitivity. Finally, it is important to clarify what is meant by the term observable universe. This phrase can be misleading, as it sounds like it refers to what we have already seen. That is not its meaning. The observable universe is technically the region of space from which light has had sufficient time to reach Earth since the Big Bang occurred. The age of the universe is approximately 13.8 billion years. Light travels at a constant speed of 300,000 kilometers, or 186,000 miles per second. Consequently, light from the most remote regions is still on its journey and has not yet arrived. The situation is made more complex by the fact that the universe has been expanding throughout the entire time that light has been traveling. When this cosmic expansion is factored into the calculations, the edge of the observable universe is determined to be about 46.5 billion light-years away from us in all directions. This gives the observable universe its total diameter of roughly 93 billion light-years. Every object located within this immense sphere is, in principle, observable to us. Its light exists and is on its way. It is theoretically possible to construct telescopes with the power to see everything, yet we have not done so. A vast portion of the observable universe has, in fact, never been observed. This ancient light is constantly streaming past our planet, but we have yet to capture it. This is the essence of the invisible universe. It is not some mysterious, dark dimension beyond our perception. It is simply the cosmos we have not yet turned our gaze toward. A specific example helps to clarify this point. In 2025, astronomers using the James Webb Space Telescope announced a significant discovery. They found over 1,700 groups of small galaxies from the early universe, existing less than 1 billion years after the Big Bang. These galaxies are exceptionally distant and dim. Before Webb, their existence was entirely unknown to us. The light from these systems has been journeying for more than 13 billion years. It washed over Earth innumerable times as humanity evolved and built civilizations. We remained unaware because we lacked infrared telescopes sensitive enough and aimed at the right patch of sky. This finding also brought a major surprise. These small galaxies seem to have been instrumental in the reionization of the universe. This was a pivotal era when the first stars ignited, and their radiation ionized the neutral hydrogen gas that permeated space. Previously, scientists believed that larger galaxies were the primary agents of this change. However, Webb's data suggests that small, faint galaxies may have been the true drivers. This demonstrates that the unseen parts of the universe are not merely more of what we already know. They hold revolutionary discoveries that can reshape our fundamental understanding. To understand our current perspective, it is helpful to look back. In the early 1900s, the very idea of galaxies beyond our own was not established. Astronomers observed hazy patches they called nebulae, but their true nature was a mystery. A famous debate took place in 1920 concerning whether these spiral nebulae were small features inside the Milky Way or vast, distant island universes. The matter was settled in 1923 by Edwin Hubble. He successfully resolved individual stars within the Andromeda Nebula. He then measured its distance to be approximately 900,000 light-years. This observation proved conclusively that Andromeda was a separate galaxy. In an instant, our conception of the universe expanded immensely. By the 1,950 seconds, photographic surveys had managed to catalogue thousands of galaxies. The 1,990 seconds ushered in a digital revolution with CCD cameras that were far more sensitive than photographic film. The Sloan Digital Sky Survey, for instance, had gathered spectra for about 2 million galaxies by 2025. This provided extensive data on their distances and characteristics. However, the SDSS survey covered only about 1/3 of the sky, and its reach into deep space was limited. The Hubble Space Telescope, which launched in 1990, completely transformed our view. Its deep field images unveiled thousands of previously unseen faint galaxies. Based on these Hubble observations, astronomers first estimated the number of galaxies to be between 100 billion and 200 billion. Then, in 2016, a new analysis using mathematical modeling drastically revised that figure. The new estimate was approximately 2 trillion galaxies. This was a 10-fold increase over the previous consensus. The reason for this change was a recognition of Hubble's limitations. It could not detect the very faintest and most remote galaxies. When astronomers used statistical methods to account for these missing populations, they concluded the universe was far more crowded than we had observed directly. This set the stage for the James Webb Space Telescope. Launched in December 2021, Webb is an infrared observatory designed to perceive the light that is invisible to Hubble. Its mirror measures 6.5 meters, or about 21 feet, across, dwarfing Hubble's 2.4 meter, or nearly 8-foot, mirror. This makes Webb substantially more sensitive. In its initial years of operation, Webb has already identified galaxies from only a few hundred million years after the Big Bang. These discoveries are actively challenging our models of how galaxies form. In 2024 and early 2025, the Euclid space mission also began releasing its data. Euclid's objective is to create a map of billions of galaxies over a vast area of the sky. During its first year, it catalogued 26 million galaxies in its deep field observations. As the mission progresses, Euclid will observe billions more. Yet, even billions of galaxies represent a small fraction of the estimated 2 trillion. We have made astonishing progress, but we have still only begun to explore the cosmos. One significant limitation is access to telescope time. Only a handful of world-class observatories are capable of studying faint, distant galaxies. These instruments are in constant demand, with intense competition among scientists for observing slots. There are simply not enough telescopes or hours in the year to look at everything. Another issue is the inherent difficulty of detecting faint sources. Galaxies that are very far away appear incredibly dim. Their light radiates outward, spreading across an ever-expanding sphere. By the time this light reaches Earth, a distant galaxy may deliver only a few photons per second to a telescope's mirror. Detecting such a faint signal requires very long exposure times. It also demands pristine conditions, dark skies far from light pollution, minimal moonlight, and a perfectly stable atmosphere. Cosmic dust presents another major obstacle. Dust within our own Milky Way galaxy effectively blocks the light from more distant objects. An area covering about 10 to 20% of the sky is obscured by the disk of the Milky Way. This region is known as the zone of avoidance. We cannot see distant galaxies through this veil using optical wavelengths. This means that a significant portion of the universe, roughly 10 to 20%, is hidden from our view by the dust in our own galactic home. It is natural to wonder what kinds of galaxies populate this invisible universe. One might assume they are simply more of the types we have already documented, but this is not the case. Our observations are subject to a distinct bias. We have a tendency to see the brightest, largest, and most massive galaxies. This is because they are the easiest to detect. A giant elliptical galaxy containing 1 trillion stars is far more conspicuous than a dwarf galaxy with just a few 100 million stars. The crucial point, however, is that dwarf galaxies are believed to be far more common. Most galaxies in the cosmos are small. We have evidence for this from studying our own local cosmic neighborhood. The local group contains the Milky Way, Andromeda, and about 80 other smaller galaxies. The majority of these members are dwarf galaxies. If this ratio is consistent throughout the universe, it suggests the vast majority of the 2 trillion galaxies are small, faint dwarfs. These systems are extremely difficult to detect over great distances. These dwarf galaxies are scientifically important. They are the fundamental building blocks that merge over cosmic time to create larger galaxies like our own. They hold important clues about the nature of dark matter. They might also be home to unusual kinds of stars or black holes. The Milky Way itself is actively consuming dwarf galaxies. The Sagittarius dwarf elliptical galaxy is currently being torn apart by our galaxy's gravity. Its stars are being stretched out into long, streaming trails. The Magellanic Clouds, visible from the southern hemisphere, are also being disrupted. They will likely merge with the Milky Way sometime in the distant future. There is an even more extreme class called ultra-faint dwarf galaxies. These tiny satellite galaxies contain only a few thousand stars, a stark contrast to the Milky Way's 100 billion. Some are so profoundly dim that the light from the entire galaxy is fainter than that of a single bright star. Within our local group of galaxies, we are aware of roughly 60 ultra-faint dwarfs. The intriguing detail is that our theoretical models predict there should be hundreds, perhaps even thousands, just in orbit around the Milky Way. This discrepancy exists only in our immediate cosmic vicinity. Throughout the universe, it is probable that trillions of these ultra-faint dwarfs contribute to the overall galaxy count while eluding our detection because they are simply too dim. There is also the matter of entirely new types of structures. In 2024, astronomers announced their discovery of the Big Ring, a truly massive circular arrangement of galaxies that spans about 1.3 billion light-years. According to our fundamental understanding of cosmology, the universe on its largest scales should be relatively uniform, which means structures of this immense size should not exist. And yet, there it is, along with another enormous formation known as the Giant Arc. These cosmic patterns were invisible until recently, not because we were unable to see the individual galaxies themselves, but because we had not yet mapped a large enough volume of space to recognize the overarching design. Looking ahead, we might ask what it will take to make more of this invisible universe visible. The answer lies in more powerful telescopes and superior technology. The Nancy Grace Roman Space Telescope is scheduled to launch in the late 2022, equipped with a field of view 100 times larger than Hubble's. Roman will observe hundreds of millions of galaxies across thousands of square degrees of the sky, giving us a far greater sense of cosmic structure. Here on the ground, the extremely large telescope is being constructed in Chile, and with a mirror 39 meters or 128 feet across, it will be the largest optical telescope in the world. The ELT will be capable of seeing fainter objects in more exquisite detail than any current telescope. At the same time, the Square Kilometre Array, being built in Australia and South Africa, will be the most sensitive radio telescope ever constructed. Its mission will be to map the neutral hydrogen gas in galaxies, revealing the invisible reservoirs of fuel from which future stars will form. But even with all these remarkable instruments working together, we will still only observe a tiny fraction of the estimated 2 trillion galaxies. Our view might expand from 0.0025% to perhaps 1 or 2%. The fundamental problem is one of time, as there are only so many hours in a day and so many nights in a year for observation. There are also specific challenges that contribute to what remains unseen. When astronomers observe the sky, they are in a constant battle with numerous sources of noise and interference. Light pollution from cities brightens the night sky, while atmospheric turbulence blurs the resulting images. The moon, when it is bright, can wash out the light from faint objects. Even the dust and gas within our own solar system generate a faint glow that must be accounted for. Even for telescopes positioned in space, high above Earth's atmosphere, significant challenges remain. Cosmic rays are constantly bombarding the detectors, creating false signals in the data. The instruments themselves generate their own electronic noise. All detectors have a dark current, which is a small signal that registers even when no light is hitting them. Every single photon that arrives from a distant galaxy must be carefully distinguished from all these sources of noise. For extremely faint objects, the authentic signal might be only slightly greater than the noise itself. This requires very long integration times, where a detector is exposed for hours or even days on end. The Hubble Ultra Deep Field, for instance, demanded over 11 days of total exposure time spread across hundreds of orbits. To observe the entire sky to this same depth with a single telescope would require an estimated 300,000 years. Then there is the challenge of simply identifying what you are seeing. A deep image might capture thousands of faint objects. The majority are galaxies, but some are stars, some are asteroids, and some are merely instrumental artifacts. Distinguishing them is a painstaking process. Galaxies generally appear as extended, fuzzy blobs, while stars look like sharp points. The complication is that very distant galaxies can also appear as points of light. Multiple observations are needed to identify asteroids, which reveal themselves by their movement. Spectroscopy is often required to definitively confirm an object's identity. For every single object that is detected, hours of careful analysis might be necessary for proper classification. Even with the help of machine learning, there is a limit to how fast this data can be processed. Millions of galaxies are currently sitting in existing data archives, unanalyzed because there are simply not enough astronomers to process everything. Our perception is also skewed by selection effects, which systematically bias our view of the cosmos. Bright objects are inherently easier to find than faint ones. Large objects are easier to resolve than small ones, and objects with certain colors tend to stand out more. These biases mean the galaxies we have observed so far are not a truly representative sample. They are skewed toward bright, large, colorful galaxies located in well-studied regions of the sky. Astronomers attempt to correct for these selection effects using statistical methods, modeling the probability of detecting various objects based on their properties. This is how we arrive at the estimate of 2 trillion galaxies, even though we have only directly observed about 50 million. The estimate is a product of observation combined with statistical correction, but these corrections carry their own uncertainties. This reality raises a more philosophical question. If we can never observe most of the universe, does it really matter? Is there value in knowing that 99.9% of galaxies are out there, even if we cannot study them individually? I believe there is. Understanding the limits of our knowledge is what keeps us humble. It reminds us that the universe is far larger and more complex than we can fully comprehend, and it is this awareness that drives us to keep exploring. There is also the practical consideration that what we have not yet seen might contain things we need to know. Suppose there is a common type of galaxy that we have never observed because it is too faint or lies in an unobserved region of the sky. Our models of the universe are built upon what we have seen. If we are missing a major component, our models might be wrong. This very thing has happened before. Dark matter was discovered because the motions of galaxies did not match expectations. We had to invent the concept of dark matter to explain our observations. What if there are other, invisible components we are currently missing? To bring this to a human scale, why should you, as a non-astronomer, care about the invisible universe? What does it matter that we have only observed a tiny fraction of all galaxies? I think it matters because it changes your perspective. We live in an age where information seems abundant, making it easy to feel like we know a lot, like we have figured most things out. The invisible universe reminds us that we have not. The cosmos is vastly larger and more complex than our everyday experience suggests, and most of what exists is beyond our current ability to study. This realization should inspire both wonder and humility. It inspires wonder at the sheer scale of the cosmos, and humility at how little we actually know, despite all our progress. It also has practical implications for thinking about life in the universe. If we have only observed 0.0025% of galaxies, then we have barely begun the search for signs of life. Every one of those galaxies contains billions of stars. It is conceivable that nearly every star hosts planets, which would mean the number of worlds with the potential for life is truly immense. If the emergence of life is not an exceptionally rare event, then it follows that the universe should be filled with it. The reality, however, is that we have examined such a minuscule portion of the cosmos that our current failure to detect any signals of life carries little weight. The unseen universe almost certainly holds life, and possibly even intelligent civilizations. We have not yet discovered them, for the simple reason that our search has not yet extended to enough places. This perspective should fill us with a renewed sense of optimism for the search for extraterrestrial intelligence. We are not exhausting the places we can look. On the contrary, we are only just beginning. The invisible cosmos contains trillions of galaxies that remain unstudied, and each one could be home to billions of habitable worlds. When one considers the sheer scale involved, the probability that we are alone seems to diminish to almost nothing. So, what have we come to understand? We know the observable universe holds around 2 trillion galaxies, yet we have only managed to observe a tiny fraction of them in any detail. We have learned about the various kinds of objects that constitute the invisible universe. We have also come to appreciate the challenges of observation, including the immense time and resources needed to detect faint and distant objects. And this has led us to ponder the philosophical and practical implications of existing in a cosmos where the vast majority of what is real remains beyond our sight. The invisible universe is enormous, far exceeding the scope of the one we have observed. For each galaxy we have closely studied, tens of thousands more await our attention. For every star that has been catalogued, there are trillions that have not. This realization should instill in us a profound sense of wonder and humility, wonder at the incomprehensible scale of it all, and humility in the face of our limited knowledge. But it should also serve as an inspiration to continue our exploration. The invisible universe is not destined to be unseen forever. It is merely unseen for now. With more advanced telescopes, increased observation time, refined techniques, and our sustained dedication, we can steadily make more of it visible. While we will never see all of it, we can always see more. We can continue to push the boundaries of our perception outward, revealing new corners of the cosmos. Thank you for accompanying me on this journey into the invisible universe. If you found this exploration to be of value, a like or subscription would be greatly appreciated, as it helps me continue creating these explorations of the cosmos. Always remember that the universe is profoundly larger than what we perceive. Each time we look, we discover something new, and that is the essential beauty of this endeavor. The invisible universe is not an empty void. It is filled with wonders that we have not yet found. It is full of galaxies waiting to be catalogued, stars waiting to be studied, and perhaps even civilizations waiting to be contacted. The frontier of cosmic exploration stretches out before us, seemingly without end. We are surrounded by mystery, and this makes our era the most exciting time to be alive and to gaze up at the stars. Good night, and I hope you never see the night sky in quite the same way again. Let us now consider the cosmic horizon, which represents the ultimate boundary of what we can perceive. Even with flawless telescopes and infinite time, there are regions of the universe that we can never observe. This is not a limitation of our technology. It is a fundamental consequence of an expanding universe and the finite speed of light. Light from extremely distant parts of the cosmos is indeed traveling in our direction. However, the universe itself is expanding faster than that light can traverse the distance between us. These remote regions are receding from our position at a velocity greater than the speed of light. This does not violate the laws of physics, as they are not moving times through time-space faster than light. Instead, the very fabric of space between us and them is stretching. The expansion of space can carry objects apart from each other faster than light can travel through that space. This means a cosmic horizon exists, beyond which we can never see. Light originating from regions beyond this boundary will never reach us. Regardless of how long we might wait or how powerful our instruments become, those areas are fundamentally invisible, severed from us by the expansion of space. The precise location of this horizon is determined by the specific details of the universe's expansion, which is driven by a force known as dark energy. Current estimations place the cosmic horizon at a distance of about 46.5 billion light-years. Everything beyond that point is forever outside our view. But what is truly strange is that the universe as a whole is likely much, much larger than the observable portion. It could even be infinite. If the universe is indeed infinite, then the observable universe, the part we can see or could ever hope to see, is an infinitesimally small fraction of the total reality. The invisible universe is not just vast, it is infinitely so. Allow me to clarify this idea with an analogy. Picture yourself standing in the middle of a great ocean, surrounded on all sides by a thick fog. You can only see for about 1 kilometer, or 6/10 of a mile, in any direction. This visible circle, 2 kilometers or 1.2 miles across, represents your observable ocean. Beyond the fog, the ocean continues, perhaps for thousands of kilometers or millions of miles. It might even extend infinitely, but you cannot see it because you are limited by the fog. Now, imagine that the fog is gradually receding, expanding outward. With every passing hour, you can see a little bit farther. But there is a twist. The ocean is also expanding. New water is being added everywhere, including in the area beyond your visible horizon. And crucially, the ocean is expanding faster than the fog is receding. So, even as your visible area grows, there is always more ocean beyond your sight. In fact, the ocean beyond your horizon is growing faster than your horizon is expanding. This is the kind of universe we inhabit. We can see farther each year as light from more distant regions finally reaches us. But the universe is expanding more rapidly than light can travel. Consequently, there will always be regions that lie beyond our horizon. This has profound implications. What it implies is that we are fundamentally isolated within the universe. There are galaxies and vast cosmic structures out there that we can never see, never study, and never communicate with. For all the interaction we could ever have with them, they might as well exist in a separate universe. This isolation is not a temporary condition, it is permanent. The cosmic horizon is a fundamental boundary, and the situation is actually worsening. Dark energy is causing the expansion of the universe to accelerate. Galaxies that are currently just inside our observable universe will eventually be carried across the horizon, disappearing from our view. In the far distant future, billions of years from now, the observable universe will contain fewer galaxies than it does today, because the accelerating expansion will have swept them beyond the cosmic horizon. Astronomers of the distant future, should any exist, will gaze upon a cosmos that appears much lonelier than the one we see today. But if we return our perspective to the present, a different picture emerges. Right now, in the year 2025, we are living through a golden age of astronomical exploration. Our telescopes are more powerful than at any point in history, and we have access to vast collections of data spanning the entire electromagnetic spectrum, from radio waves to gamma rays. We can run computer simulations that trace the evolution of the universe in extraordinary detail, supported by a global community of thousands of scientists all working to decipher the cosmos. Despite this incredible progress, the invisible universe remains immense. The galaxies we have observed are but a tiny fraction of all that is out there. Most of the cosmos remains unseen, a vast frontier still waiting to be discovered. To give a sense of what we are missing, consider a few specific examples. Dwarf galaxies, as noted, are likely the most numerous type of galaxy in the universe, yet their faintness makes them exceedingly difficult to spot at great distances. Within our own local group, we are aware of approximately 80 galaxies, the majority of which are dwarfs, but our census continues to grow. As recently as 2020, astronomers identified new dwarf galaxies in orbit around the Milky Way. These are galaxies in our immediate cosmic neighborhood, even closer than Andromeda, and we are still finding them because they are so dim. If we are still discovering new galaxies this close to home, one can only imagine the countless multitudes we are failing to see at cosmological distances billions of light years away. The invisible universe is almost certainly teeming with these small, faint galaxies. Then there are the ultra-diffuse galaxies. These are intriguing structures that can be as large as the Milky Way in diameter, but contain substantially fewer stars. Their stellar populations are spread thin, rendering them faint and very challenging to detect. Our knowledge of ultra-diffuse galaxies is only about a decade old. The first examples were found in the Coma cluster back in 2015. Since that time, hundreds more have been identified, but their true numbers could be in the millions or even billions. They form a part of the invisible universe simply because their diffuse, faint nature makes them difficult to see, even with excellent telescopes. The cosmos also contains galaxies within its great voids. The universe possesses a large-scale structure that is often described as a cosmic web. Rather than being spread uniformly through space, galaxies are concentrated along filaments and within clusters, separated by enormous, empty regions known as voids. These voids can span hundreds of millions of light-years. While not entirely empty, they do contain galaxies, but these are rare and isolated. Because they reside in areas of space that our surveys do not often prioritize, many of them remain undiscovered. The invisible universe, therefore, includes these solitary galaxies drifting through the cosmic emptiness. Furthermore, some galaxies are hidden from view by intervening dust, either within our own galaxy or in other galaxies that lie between us and them. The zone of avoidance, which is the region of the sky obscured by the disk of the Milky Way, is estimated to conceal 100 million galaxies that we cannot observe in optical light. While we can perceive some of them using infrared or radio wavelengths, a great many remain completely invisible. In a similar way, if a dusty galaxy is positioned between us and a more distant one, this foreground object can block our line of sight, hiding the background galaxy. This effect is known as obscuration, and it accounts for another portion of the invisible universe. Let's consider how the expansion of the observable universe influences what we are able to see. It was mentioned earlier that the observable universe is about 93 billion light-years in diameter, even though the universe itself is only 13.8 billion years old. This might seem like a contradiction. How is it possible to see light from objects that are 93 billion light-years away when that light has only had 13.8 billion years to travel? The resolution to this puzzle lies in the fact that space itself has been expanding during the light's journey. When light departed from a distant galaxy 13 billion years ago, that galaxy was significantly closer to us, perhaps only a few billion light-years away. However, as the light traveled toward us, the space between us and the galaxy expanded, carrying the galaxy much farther away. By the time the light finally reaches our telescopes, that galaxy is now approximately 46 billion light-years from us. And because space is symmetrical, there are galaxies just as far away in the opposite direction, which gives the observable universe its 93 billion light-year diameter. This expansion has another critical consequence. It stretches the light as it travels. This is the phenomenon of redshift. Light from a galaxy that is receding from us due to cosmic expansion gets stretched to longer wavelengths. Visible light might be elongated into the infrared, and ultraviolet light might be shifted into the visible part of the spectrum. The farther a galaxy is, the faster it moves away, and the more its light is redshifted. For the most distant galaxies, such as those studied by the James Webb Space Telescope, the redshift is extreme. Light that was emitted as ultraviolet radiation now arrives at Earth as deep infrared. This is precisely why infrared instruments like Webb are so essential for studying the early universe. The galaxies are so far away and receding so quickly that their light has been shifted entirely out of the visible range. But redshift does more than just alter the wavelength of light. It also makes galaxies appear fainter. The energy of light is tied to its wavelength. When light is redshifted, its energy diminishes. A photon that began its journey from a distant galaxy as high-energy ultraviolet light will arrive at Earth as low-energy infrared light. This means that distant galaxies appear dimmer than they would if the universe were static. When this effect is combined with the natural dimming that occurs over vast distances, it makes very remote galaxies incredibly faint. They are emitting an abundance of light in their own local frame of reference, but by the time that light reaches us, it has been so redshifted and dimmed that it requires our most sensitive instruments to detect it at all. This is another fundamental reason why so much of the universe remains invisible. The galaxies are out there, shining brightly, but their light is so weakened by its long journey that we can barely perceive it. Finally, there is the issue of cosmic variance. When we observe a small patch of the sky, we are only seeing a snapshot of that specific region. The universe, however, is not perfectly uniform. Some areas contain more galaxies than others, while some regions host different types of galaxies. If we limit our observations to a small area, we risk obtaining a sample that is not representative of the whole. Imagine trying to understand the geography of Earth by looking at a single square kilometer, or about 4/10 of a square mile. Imagine trying to comprehend our entire planet by studying just one small, randomly chosen area. If your sample landed in the middle of an ocean, you might surmise that Earth is a world of water, devoid of land. If it fell within a vast desert, your conclusion would be that our planet is entirely arid and lifeless. To build an accurate understanding, you would need to gather data from many different locations. This same principle applies to the cosmos. To grasp the full diversity of galaxies and the grand structures they form, we must observe enormous volumes of space. Yet, a fundamental challenge arises. The deeper into space we peer, the further back in time we are looking, and the smaller the volume we can survey in high detail. This presents a constant trade-off in astronomy. We can choose to look deep, or we can choose to look wide, but achieving both at once is exceptionally difficult. The Hubble Ultra Deep Field, for instance, gazed incredibly far back into cosmic history, revealing galaxies from the universe's infancy, but it did so by focusing on a minuscule patch of the sky. In contrast, the Sloan Digital Sky Survey mapped a huge portion of the heavens, covering about a third of the sky, but its view was not as deep. It consequently missed the faintest and most remote galaxies. In an ideal world, we would survey the entire sky with the same depth as the Hubble Ultra Deep Field, but with our current technology, such a project would require thousands of years to complete. We are therefore compelled to make choices. We can either study a few select regions with extraordinary detail, or survey large areas more superficially. While both strategies are valuable, they each leave parts of the invisible universe unmapped. A recent discovery offers a powerful illustration of just how much we might be missing. In 2023, astronomers revealed the existence of a colossal galaxy cluster named El Gordo, a Spanish phrase meaning the fat one. This structure is located approximately 7 billion light-years away and is home to thousands of individual galaxies, making it one of the most massive clusters ever identified. The intriguing detail, however, is not just its size, but how it was found. El Gordo was not discovered through a conventional deep optical survey. Instead, its presence was inferred from its effect on the cosmic microwave background, the faint afterglow of radiation from the Big Bang. The intensely hot gas within the cluster scatters this ancient microwave radiation, creating a subtle signature that can be detected from Earth. After finding this signal, astronomers used optical telescopes to confirm the cluster's existence. This detection method, known as the Sunyaev-Zeldovich effect, provides a way to find massive galaxy clusters that might otherwise be overlooked by optical searches. It serves as another vital tool for revealing the invisible universe, demonstrating how different wavelengths and techniques can unveil structures we never knew were there. There is also the dimension of time to consider. The universe has existed for 13.8 billion years. And when we observe distant galaxies, we are seeing them as they were billions of years in the past. The light from a galaxy 10 billion light-years away, for example, presents us with an image of that galaxy as it appeared 10 billion years ago. In the immense span of time since that light began its journey, the galaxy has continued to evolve. It might look completely different today. Countless stars have been born and have since died. It may have merged with other galaxies, or perhaps its shape has transformed from a spiral into an elliptical. We cannot witness any of these changes because the light that would show us the galaxy's current state will not reach our planet for another 10 billion years. In a very real sense, the present condition of the distant universe remains invisible to us. We can only ever see its past. The invisible universe, therefore, includes not only the galaxies we have yet to observe, but also the contemporary state of the galaxies we have already seen. This reality creates a fascinating situation for cosmologists. When we construct a map of the universe showing the locations of all the known galaxies, we are not creating a snapshot of the cosmos as it exists right now. What we are making is a map of the universe as it was at different moments in its history. A galaxy situated 1 billion light-years from us is depicted as it was 1 billion years ago. A galaxy 10 billion light-years away is shown as it existed 10 billion years ago. This is much like assembling a family photo album where each person's picture was taken in a different year. Your own photo might be from today, while your siblings is from 5 years ago. your parents from 20 years ago, and your grandparents from 50 years ago. Such an album does not represent the family as they are in a single moment, but rather presents a composite view across different times. Our maps of the universe are precisely this. They are composites of the cosmos at different epochs. The true, simultaneous present state of the entire universe is fundamentally invisible to us, simply because light has not had enough time to deliver that information. Let's now turn to the role of dark matter and dark energy within this invisible universe. When astronomers speak of what we cannot see in the cosmos, they are often referring to these two mysterious components. They are constituents of the universe that do not emit any light, which means we cannot see them directly. We only know of their existence through their gravitational effects. Dark matter accounts for about 27% of the universe's total energy density. Normal matter, which is the substance of stars, planets, and ourselves, makes up only about 5%. Dark matter does not interact with light. It neither emits, absorbs, nor reflects it, rendering it invisible to all of our telescopes. We know it must be there because galaxies and galaxy clusters possess far more mass than can be explained by their visible matter alone. This additional mass is attributed to dark matter. Dark energy is an even more perplexing phenomenon, constituting about 68% of the universe's total energy density. It is a mysterious force that is causing the expansion of the universe to accelerate. We do not know what dark energy is, and we cannot see or detect it directly. We only infer its existence because the universe is expanding faster than it should based on the amount of matter we can account for. So, in a very tangible sense, 95% of the universe is invisible. This is not invisibility in the sense that we have not yet observed it, but rather an invisibility that stems from the fact that it does not emit light, and we currently have no way to detect it directly. This represents a different kind of invisible universe. It is not composed of galaxies we have not yet looked at, but of components that are fundamentally different from normal matter and may be impossible to ever observe directly. For the purpose of this discussion, however, my focus remains on the galaxies we have not yet observed the normal matter component of the universe that does emit light, but which we simply have not yet seen. Even within that 5% of the universe that is normal matter, we have only observed a tiny fraction. When you consider this, the invisible universe becomes even larger. Not only have we observed less than 1% of the galaxies in the observable universe, but those galaxies represent only about 5% of the total cosmic content. The remainder is dark matter and dark energy, which are completely imperceptible to our telescopes. The universe is far more invisible than most people realize. Now, let us consider what all of this might mean for the search for extraterrestrial life. When we consider that the observable universe is estimated to hold as many as 2 trillion galaxies, and that we have examined only a few million of them with any real scrutiny, a profound question arises about our search for life beyond Earth. The probability that we have already discovered all existing life seems remarkably low. Within each of these galaxies, billions of stars reside, and a great number of them host planetary systems. Data gathered by pioneering missions like Kepler and TESS has fundamentally shifted our understanding, revealing that planets are not cosmic rarities, but common features of the galaxy. It now appears that most stars have at least one planet, with many possessing entire families of worlds. If even a small percentage of these planets are habitable, and if life can indeed emerge under the right conditions, the cosmos could very well be teeming with organisms. And yet, our direct search for biological signatures has been limited to a mere handful of planets. Our efforts have included listening for radio signals from stars in our cosmic neighborhood, but this survey has covered only a minuscule portion of the sky, and for a very brief period. The endeavor known as the Search for Extraterrestrial Intelligence, or SETI, can be compared to an immense communications challenge. It is like attempting to make a phone call without knowing the number, the language spoken, or which of the billions of possible frequencies is being used. From a statistical standpoint, it seems highly probable that the invisible universe harbors life. It would be a truly astonishing outcome if Earth were the sole living world. The central challenge, however, lies in the extraordinary difficulty of detection across such unimaginable distances. Any signal from a distant civilization would be extraordinarily faint by the time it reached us, and we remain uncertain about the very nature of the signs we should be seeking. Could they be using radio waves, lasers, or perhaps a medium of communication entirely beyond our current comprehension? It is conceivable that the invisible universe is populated with advanced civilizations, their presence hidden from us simply because our search has not yet extended to the right locations, the right wavelengths, or for a sufficient duration. This potential for discovery is one of the most compelling aspects of our exploration into the unseen cosmos. Each new galaxy we observe, and every new planet we investigate incrementally, raises the possibility of finding signs of life. This brings us to the fascinating field of citizen science and the way it empowers ordinary people to participate in exploring the invisible universe. The sheer volume of data gathered by modern telescopes far exceeds what professional astronomers can analyze on their own. This deluge of information, while a challenge for professionals, creates a remarkable opportunity for citizen scientists to make meaningful contributions. Through projects like Galaxy Zoo, anyone with an internet connection can help classify galaxies by viewing images online, with no specialized training required. The process is straightforward. The website presents a galactic image and poses basic questions, such as whether its shape is spiral or elliptical, or if its texture is smooth or features distinct structures. These individual classifications are then aggregated with submissions from thousands of other participants, providing a rich dataset that astronomers use to better understand galactic populations. The success of Galaxy Zoo is remarkable, having led to the classification of millions of galaxies, a feat unattainable by professional astronomers working in isolation. It demonstrates a powerful way for anyone to help make the invisible universe more visible. A similar initiative, Planet Hunters, invites participants to examine light-curve data from the Kepler and TESS missions. The task involves searching for the subtle, periodic dips in starlight that can signal a planet passing in front of its host star. Through this method, citizen scientists have successfully identified dozens of exoplanets, including some that were overlooked by automated detection algorithms. Many other such projects exist for tasks like finding asteroids, categorizing supernovae, and mapping the moon's surface. These efforts underscore that cosmic exploration is not an exclusive domain for professionals. By participating, you are helping to render the invisible universe just a little less invisible. To appreciate the immense scale we are dealing with, it is helpful to consider the cosmic web. At the grandest levels, the universe is organized into a structure resembling a vast, three-dimensional lattice. Galaxies are not scattered randomly, but are instead concentrated along immense filaments, which are thin strands of matter stretching for hundreds of millions of light-years. At the intersections of these filaments, dense clusters containing thousands of galaxies form, while in between these structures lie enormous, nearly empty regions known as voids. This intricate cosmic architecture is the long-term result of gravity acting upon minuscule density variations in the primordial universe. Areas that began with slightly more matter gravitationally attracted more material over billions of years, eventually growing into the filaments and clusters that are observable today. The intriguing detail, however, is that our maps of the cosmic web are far from complete. We have charted its structure in only small sections of the cosmos, meaning the majority of this web remains invisible to us simply because we have not yet observed a sufficient number of galaxies to reveal its full, overarching pattern. It is akin to trying to comprehend the design of an entire spiderweb by examining just a few small segments. One might see an individual strand or a junction, but the complete design would remain elusive. This is our current situation. While we have mapped portions of the cosmic web and can use computer simulations to model its theoretical appearance based on our understanding of gravity and dark matter, truly observing it requires charting millions of galaxies across vast volumes of space. What this means is that the invisible universe contains the full, magnificent tapestry of the cosmic web, the ultimate large-scale structure of existence. We will only perceive its full grandeur once our observations have encompassed a vastly greater number of galaxies than they have to date. Observing the early universe presents its own unique set of challenges. The James Webb Space Telescope was engineered precisely for this purpose, to study the very first galaxies that formed after the Big Bang. These primordial galaxies are at immense distances, meaning their light has journeyed for more than 13 billion years to reach our instruments. Over this vast cosmic expanse, the light has been stretched by the expansion of the universe, shifting it into the infrared part of the spectrum. While Webb is designed to detect this infrared light, significant obstacles remain. The galaxies themselves are extraordinarily faint and small, containing far fewer stars than their modern counterparts. Moreover, they are often shrouded in a fog of neutral hydrogen gas, which absorbs their ultraviolet light and makes them even more difficult to perceive. Despite these difficulties, Webb has already identified hundreds of these ancient galaxies, and its findings have been surprising. Some appear larger and more luminous than our models predicted, while others exhibit astonishingly high rates of star formation. These discoveries are actively challenging our current understanding of how galaxies are born and how they evolve over time. Yet, even a telescope as powerful as Webb can only discern the most brilliant of these early galaxies. It is likely that millions, or perhaps billions, of fainter, nascent galaxies exist below Webb's detection threshold. They remain a component of the invisible universe, their secrets awaiting discovery by a future generation of more powerful telescopes. A particularly dynamic area of modern astronomy involves the study of transient events, phenomena that appear or change with sudden intensity. Consider supernovae, the explosive final moments of massive stars, which can briefly generate more light than the billions of other stars in their host galaxy combined. Gamma-ray bursts represent the most energetic explosions known, capable of releasing more energy in seconds than our Sun will produce over its entire lifespan. And when a star ventures too close to a black hole and is torn asunder, the resulting tidal disruption event creates a brilliant flare of light that can persist for months. Across the cosmos, such phenomena unfold continuously, yet our awareness is confined only to the specific regions we happen to be monitoring. The unseen universe is filled with innumerable fleeting events that pass by unobserved, simply because our gaze is directed elsewhere at that particular instant. An endeavor known as the Zwicky Transient Facility methodically scans the northern skies every few nights, searching for precisely these kinds of temporary celestial changes. It has successfully identified thousands of supernovae, asteroids, and other variable objects, but its reach is ultimately limited to our cosmic neighborhood. Transient events occurring in faraway galaxies remain too dim for the majority of current surveys to register. This invisible universe is brimming with explosions and eruptions that we are never witness to. Every single night, thousands of stars detonate in galaxies billions of light years from Earth, and most of these cosmic finales go entirely unnoticed. They occur, they diminish, and no one on our world is ever aware of their passing, consigning them to the vastness of the unseen cosmos. To place this into a clearer perspective, it is helpful to consider one final thought. The observable universe encompasses everything we could ever possibly see, representing the full expanse of space from which light has had enough time to reach us. Within this immense volume, there are an estimated 2 trillion galaxies, yet we have only managed to study a tiny fraction of them in any significant detail, perhaps 50 million out of that 2 trillion total. This amounts to a mere 0.0025%. The implication is that for each single galaxy that has captured our scientific attention, another 40,000 remain unexamined, and this figure only accounts for the galaxies we are aware of. There may well be entire classes of structures or objects we have not yet discovered, because we simply haven't observed a large enough portion of the universe to encounter them. The scale of the invisible universe is beyond easy comprehension. It is not some remote, inaccessible place. Rather, it is a reality that surrounds us completely, filling the sky in every direction. At this very moment, light from these uncatalogued galaxies is streaming past our planet, continuing its journey through space towards some other vantage point where an observer might one day see what we have missed. In the decades to come, new telescopes and ambitious surveys will begin to reveal more of this hidden cosmos. The Roman Space Telescope is set to survey billions of galaxies, while the extremely large telescope will perceive objects fainter and more distant than ever before. At the same time, the Square Kilometre Array will chart the universe at radio wavelengths. To process the mountains of data these instruments will generate, we will rely heavily on artificial intelligence and machine learning. With these tools, we might increase our detailed galactic census from 0.0025% to perhaps 1%, or even a few percent. While this represents remarkable progress, It also means that 95% or more of the universe will persist beyond our detailed view. We will still only be scratching the surface. This, however, is perfectly acceptable. The invisible universe does not represent a failure, but a challenge. It is an invitation. It serves as a quiet reminder that the cosmos is far larger and more intricate than we can ever fully grasp. Every galaxy we manage to observe, every star we study, and every planet we discover contributes to our growing body of knowledge. We are assembling a picture of the universe one observation at a time. It is a portrait that will never be complete, but it becomes richer and more detailed with each passing year. The invisible universe will always be present, beckoning us and challenging us to look deeper, to engineer better instruments, and to formulate more insightful questions. So, the next time you gaze upon the night sky and see those few thousand stars, take a moment to remember what you are not seeing. You are not seeing the 100 billion other stars that constitute our own galaxy. You are not seeing the 2 trillion other galaxies that lie beyond the Milky Way. You are not seeing the cosmic web, the grand, filamentary structure that organizes all matter. You are not seeing the countless dwarf galaxies, the ultra-diffuse galaxies, the galaxies in cosmic voids, or those concealed by veils of dust. You are not witnessing the supernova explosions happening right now in distant star systems. You are not seeing the planets in orbit around other suns, nor any potential civilizations that might inhabit them. All of that is imperceptible to your eyes, and yet it is there. The invisible universe envelops us, patiently awaiting discovery. We have made incredible strides in the centuries since we first realized that other galaxies exist. We have charted millions of them, measured the expansion of the universe, and uncovered the profound mysteries of dark matter and dark energy. Our catalogues now include thousands of exoplanets, and we have peered back to the dawn of the cosmos, seeing galaxies as they formed when the universe was young. But we have only just begun. The unseen cosmos is vast, containing mysteries we cannot yet even imagine. And that is precisely what makes the pursuit of astronomy so compelling. There is always more to discover, always another galaxy to observe, and always another question to answer. The universe possesses an infinite capacity to surprise us, and the great majority of it remains invisible, waiting for the next generation of astronomers to reveal its secrets. Now, let us delve more deeply into specific examples of what constitutes this invisible universe. Understanding the details helps us appreciate the sheer scope of what we are missing. I want to guide you through different categories of objects and structures that exist but remain largely unobserved. Each category represents a vast population of cosmic entities that we know must be out there, but which we have barely begun to catalogue. First, let us consider low-surface brightness galaxies. These are stellar systems that are incredibly spread out and diffuse. They can contain a great number of stars, sometimes as many as the Milky Way, but those stars are distributed across a much larger volume of space. This characteristic makes them extremely faint per unit area of the sky. Imagine 2 sources of light. One is a bright spotlight, concentrating its light into a small, intense area. The other is a dim flood lamp, spreading the same total amount of light over a much wider expanse. From a distance, the spotlight is easy to see, while the flood lamp is barely visible. Low-surface brightness galaxies are like these cosmic flood lamps. They are present and emitting light. But that light is spread so thinly that they are incredibly difficult to detect. These galaxies were largely unknown until the 1980 seconds. Astronomers had missed them for decades because standard survey techniques were optimized to find bright, compact objects. When researchers finally began to look specifically for diffuse galaxies, they discovered them everywhere. Today, we know of thousands of low-surface brightness galaxies, but there are probably billions in the observable universe. Most remain invisible simply because they are so faint. Standard galaxy surveys do not detect them unless they happen to be very close to us. The invisible universe therefore contains vast numbers of these ghostly galaxies, so diffuse they are almost transparent. There is also a special class of ultra-faint dwarf galaxies that are even more extreme. In the gravitational embrace of larger galaxies, like our own Milky Way and the neighbouring Andromeda, exist much smaller cosmic islands, known as ultra-faint dwarf galaxies. What is so striking about these tiny satellite systems is their sheer scarcity of stars, often containing just a few thousand in total. This figure stands in stark contrast to the vast stellar census of the Milky Way, which is estimated to hold 100 billion stars or more. Some of these ultra-faint dwarfs are so profoundly dim that their collective light is outshone by a single, brilliant star, placing them among the most minimally luminous objects in the entire universe that we would still classify as a galaxy. Astronomers have so far identified about 60 of these ghostly galaxies within our local group. Yet, our theoretical models of galaxy formation tell a different story, one that suggests hundreds, or possibly even thousands, should be quietly orbiting the Milky Way alone. The reason we have not yet found them is a simple consequence of their nature. Their incredible faintness means they can only be revealed through deep, patient observations using the world's most powerful telescopes. And this is merely the picture in our immediate cosmic vicinity. When we look out across the vast expanse of the universe to other galaxy groups and clusters, the number of these ultra-faint dwarfs likely swells into the trillions. They represent a significant portion of the invisible universe, a silent contribution to the total galaxy count, yet they remain hidden from our view, their light too feeble to be detected. Another fascinating component of this hidden cosmos involves intergalactic stars, which are sometimes referred to as intracluster stars. These are suns that have no galactic home. They are adrift in the immense, dark voids between the galaxies, wandering either as solitary points of light or in loosely associated groups. The story of how a star ends up in such isolation is one of cosmic upheaval, unfolding during the slow, powerful dance of galactic collisions and mergers. As two galaxies gravitationally interact, the tidal forces involved can act like a slingshot, ejecting stars at tremendous speeds. These stars achieve escape velocity, leaving their parent galaxies behind to begin a long journey through intergalactic space. Within the dense environments of galaxy clusters, where hundreds or even thousands of galaxies are bound together by their mutual gravity, vast populations of these orphan stars can accumulate over cosmic time. Indeed, observations of nearby galaxy clusters have revealed a surprising fact. Somewhere between 10 and 40% of the total starlight in these massive structures emanates not from the galaxies themselves, but from this diffuse population of intracluster stars. This represents an enormous number of stars that are exceptionally difficult for us to observe directly. Because they are not gathered into the concentrated forms of galaxies, their light is spread thinly across immense volumes of space, rendering them extraordinarily faint. The invisible universe is therefore home to uncounted trillions of these wandering stars. They are out there, tracing orbits within the gravitational potential of galaxy clusters, but we can only barely perceive their collective glow even in the clusters closest to us. For more distant clusters, they are completely beyond the reach of our current telescopes. This points to a significant fraction of all the stars in the universe that are simply not included in our standard galactic inventories. When we attempt to count the galaxies, we are invariably missing the vast numbers of stars that have been expelled from them. The situation could be compared to trying to take a census of Earth's population by only counting individuals who are inside buildings, completely overlooking everyone who happens to be outside. The search for the unseen also takes us back to the very dawn of time, to the question of primordial galaxies. These are the very first galaxies that began to shine in the young universe, and the James Webb Space Telescope was specifically designed to find them. In this mission, it has achieved remarkable success. Within its first couple of years of operation, Webb has managed to identify galaxies that existed when the cosmos was merely a few 100 million years old, giving us our clearest views yet of these earliest galactic structures. But even an instrument as powerful as Webb has its fundamental limits. The smallest and most faint of these primordial galaxies still lie beyond its detection threshold. These first, tiny galaxies might have been quite modest, perhaps containing only a few million stars. While this would have been enough stellar firepower to ionize the gas in their immediate surroundings, their collective light would be far too faint for us to see directly across such vast cosmic distances. Our models of cosmic evolution strongly suggest that immense numbers of these small primordial galaxies must have existed. They may have served as the fundamental seeds, the building blocks that gradually merged together over billions of years to form the large, mature galaxies we see today, including our own Milky Way. This matters profoundly because these invisible primordial galaxies are thought to have played a critical role in cosmic history. They were likely responsible for reionization, the pivotal process that transformed the universe from an opaque fog into the transparent state we know today. Without a proper understanding of these tiny, early galaxies, we cannot assemble a complete picture of how the universe evolved from its smooth, nearly uniform beginnings after the Big Bang into the richly structured cosmos we inhabit. The full story of cosmic dawn, that transformative era when the very first stars and galaxies began to illuminate the darkness, is written in the existence of these galaxies. With Webb, we are now reading the first few sentences of that story, but most of the intricate details remain concealed from us. To appreciate the scale of this invisible universe, it helps to understand how galaxies themselves are arranged. Most galaxies do not exist in isolation. Instead, they are found in groups or much larger clusters, all bound together by the persistent force of gravity. Our own Milky Way is a member of what we call the Local Group, a collection that includes the Great Andromeda Galaxy, the smaller Triangulum Galaxy, and about 80 other, smaller galactic systems. This cosmic neighborhood of ours spans a region of about 10 million light-years, or roughly 6 million miles across. Beyond the Local Group, the universe is filled with thousands of other galaxy groups, as well as hundreds of truly massive galaxy clusters. Any one of these clusters might contain hundreds, or even thousands, of individual galaxies. The Virgo cluster, which is the nearest large cluster to our own group, is home to over 2,000 galaxies. Farther away, the Coma cluster contains over 1,000. These immense assemblies are the largest structures in the universe that are held together by their own gravity. But the crucial point is this: while we have managed to catalogue the visible galaxies in nearby clusters with reasonable accuracy, there is much more to the story. The Virgo cluster is situated at a relatively close 53 million light-years, a proximity that allows us to perceive even its less luminous member galaxies. Most galactic clusters, however, are located at far greater distances from Earth. As we peer deeper into space, our view becomes limited to only the most brilliant objects within these distant clusters. This means the faint dwarf galaxies, which actually represent the majority of a cluster's population, become completely undetectable. What emerges is a significant bias in our catalogues of faraway galaxy clusters, which are skewed to feature only the largest and brightest galactic structures. We are effectively missing the vast majority of the galaxies that belong to these ancient systems. The concept of an invisible universe begins here, with the complete populations of galaxy clusters that we know must exist based on nearby examples like Virgo, but which remain beyond our observational reach across immense cosmic distances. Another critical factor to consider is the evolution of galaxies over the lifespan of the cosmos. Galaxies are not static entities. They undergo profound transformations. They merge with one another, ignite the formation of new stars as old ones fade, and experience constant inflows and outflows of gas. The galaxies we observe in the distant universe, seen as they were billions of years in the past, appear quite different from their modern counterparts. These early galaxies tend to be smaller, possess more irregular shapes, and are characterized by much more vigorous rates of star formation. In contrast, galaxies in the nearby universe are typically larger, have settled into more organized spiral or elliptical forms, and create stars at a more measured pace. This evolutionary process is a cornerstone for comprehending cosmic history. Yet, to truly grasp it, we require observations of enormous numbers of galaxies at various distances, which correspond to different epochs in time. To build a complete picture, we need statistical samples of thousands or even millions of galaxies from each era to understand the full spectrum of their characteristics and how they shift over eons. The fundamental problem is that we lack this comprehensive data for most of cosmic history. While we possess good samples of nearby galaxies and reasonable data from a few specific past epochs targeted by dedicated surveys, vast gaps in our knowledge remain. For instance, we have a scarcity of detailed observations of galaxies from the period 8 to 10 billion years ago, a pivotal time when many were transitioning from active star-forming phases to more quiescent states. The invisible universe, therefore, also contains all these unobserved galaxies at intermediate redshifts. These are the very galaxies that would fill in the story of cosmic evolution, but they remain unseen because our surveys have not yet been deep enough to capture them at those specific distances. Let's explore a more local aspect of this invisibility, the Milky Way's zone of avoidance. Our home galaxy is a disk composed of stars, gas, and interstellar dust, spanning about 100,000 light-years in diameter, but only about 1,000 light-years thick through most of its expanse. Our solar system is situated within this disk, approximately 26,000 light-years from the galactic center. When we direct our telescopes toward the core of the galaxy or along the flat plane of the disk, our line of sight must penetrate tremendous quantities of this dust. The dust acts as a veil, absorbing and scattering light, especially at shorter blue and ultraviolet wavelengths. The effect is akin to trying to see through a dense fog, where distant objects become obscured and everything appears dimmer and redder than it truly is. This phenomenon creates what is known as the zone of avoidance, a band across the sky where our view of distant galaxies at optical wavelengths is almost completely blocked. This zone is roughly 20 degrees wide and is centered on the galactic plane. While that might not seem extensive, it effectively conceals about 10% of the entire celestial sphere. Within this obscured region, it is estimated that anywhere from 100 million to several hundred million galaxies are hidden from our optical view. We can identify some of them using infrared or radio wavelengths, as these longer waves are better at penetrating the dust. However, surveys conducted in the infrared and radio spectra generally lack the depth and resolution of their optical counterparts. As a result, the majority of these galaxies remain either poorly understood or entirely invisible to us. This observational blind spot has real-world implications. It is possible that massive galaxy clusters are concealed behind the Milky Way's disk, or that there are nearby galaxies we simply do not know exist. In fact, by using radio and infrared observations, astronomers have already uncovered several relatively close galaxies that were hidden within the zone of avoidance. A notable discovery occurred in 1994 with the identification of the Dwingaloo 1 galaxy, a spiral galaxy a mere 10 million light-years away. This is closer than many well-known galactic neighbors, yet it had been obscured by the dust of our own galaxy for decades. If we are still finding galaxies this near to us, hidden in our own cosmic backyard, one can only imagine what we are missing at greater distances. The invisible universe thus includes everything that lies behind this zone of avoidance. These objects are not inherently invisible. They are simply hidden from our particular vantage point inside a dusty galaxy. From a location outside the Milky Way, these galaxies would be clearly visible, but for now, we are confined within it. Until we can deploy telescopes to positions far from the galactic plane or devise superior methods for peering through the dust, this significant portion of the universe will remain concealed. Quasars offer another fascinating perspective on the invisible universe. These are extraordinarily luminous objects, powered by supermassive black holes residing at the centers of galaxies. As gas spirals into the black hole, it heats to incredible temperatures and radiates immense amounts of light, sometimes outshining its entire host galaxy. When quasars were first discovered in the 1960 seconds, they were a profound mystery, as astronomers could not explain their nature or their incredible brightness. Today, we understand that a quasar represents a specific phase in the life of a galaxy. When a galaxy has an abundant supply of gas to feed its central black hole, it can light up as a quasar. Once this fuel source is depleted, the quasar's light fades, leaving behind a normal galaxy with a dormant supermassive black hole at its core. The great brilliance of quasars makes them valuable tools for studying the invisible universe. We can detect them at enormous distances, much farther than we can see ordinary galaxies. The most distant quasars yet found date back to a time when the universe was less than 1 billion years old, over 13 billion years ago. The existence of these quasars tells us that supermassive black holes, with masses millions or billions of times that of our Sun, had already formed very early in cosmic history. This is a surprising finding, as our current models do not fully explain how black holes could grow so massive so quickly, but an intriguing detail emerges from these observations. For every single quasar we can detect at such a distance, there are likely hundreds or even thousands of normal galaxies at the same cosmic depth that we cannot see because they are not bright enough. The quasar acts like a brilliant lighthouse, easy to spot across the vast cosmic ocean, while the ordinary galaxies are like small boats with faint lanterns, rendered nearly invisible by the darkness. This means that quasars provide a skewed perception of the early universe. We are able to see the most extreme and active galaxies simply because their brightness allows them to be detected. In doing so, we are missing the bulk of the galactic population, the typical galaxies quietly going about their existence, not actively fueling a central black hole. The high redshift universe, a realm of immense distance and early time, is thought to be overwhelmingly populated by ordinary galaxies. We infer their existence because their descendants are the galaxies we see around us in the local cosmos. Yet, seeing them directly is a task of extraordinary difficulty. Even the powerful Webb telescope is only able to provide a preliminary glimpse into this population. This is where a remarkable cosmic phenomenon offers a unique window. It is known as gravitational lensing, and it helps us see into the otherwise invisible universe. Gravitational lensing is a direct prediction of Einstein's theory of general relativity. The theory describes how any object with mass bends the fabric of space-time around it. Light, in its journey across the cosmos, must then follow these curved pathways. Imagine an exceptionally massive object, like an entire cluster of galaxies. If it happens to lie directly along our line of sight to a more distant galaxy, its immense gravity will bend and redirect the background galaxy's light. This process acts as a natural magnifying glass. It makes the distant object appear significantly brighter and larger than it would be on its own. In certain alignments, the lensing effect is so pronounced that it can distort the background galaxy into elongated arcs of light. It can even create multiple, distinct images of the very same object. Astronomers have learned to leverage this effect, using these massive clusters as cosmic telescopes. By carefully studying these lensed galaxies, they can observe objects that would otherwise be far too faint for even our most advanced instruments to detect. The magnification can be substantial, often boosting a galaxy's apparent brightness by a factor of 10, and in some cases, by 100 times or more. This technique has been instrumental in discovering some of the most remote and dimmest galaxies ever identified. Without the fortunate alignment that produces lensing, these ancient galaxies would remain completely hidden from us. They would be a part of the vast invisible universe. Lensing effectively brings them out of the shadows and into our view. However, such perfect alignments are exceedingly rare. A massive galaxy cluster must be positioned with incredible precision between Earth and a background source. Consequently, the great majority of distant galaxies are not lensed. They continue to be invisible to us. To find these rare cosmic alignments, astronomers undertake extensive surveys. They meticulously scan the skies around known massive clusters. Programs like the Hubble Frontier Fields Initiative, for instance, dedicated enormous resources to observing 6 such clusters in unparalleled detail. Their specific goal was a simple one. They wanted to find and study the lensed galaxies hiding behind them. These efforts were successful, uncovering hundreds of previously unknown background galaxies. They revealed entire populations that would have otherwise gone completely unnoticed. Still, what stands out is that this represents only a minuscule fraction of the whole. For each lensed galaxy that we are fortunate enough to discover, there are likely thousands more at comparable distances that remain unlensed and therefore unseen. They are a fundamental component of the invisible universe, patiently awaiting a chance lensing event or the arrival of next-generation technology to finally reveal them. Let us now turn our attention to the cosmic microwave background, which offers a very different perspective on the invisible universe. The cosmic microwave background, or CMB, is the most ancient light we can observe. It is essentially the residual heat from the Big Bang, a faint glow of radiation that was released approximately 380,000 years after the universe began. This moment, known as recombination, marks a critical transition. The cosmos cooled sufficiently for electrons and protons to bind together, forming neutral hydrogen atoms for the first time. Before this event, the universe was a hot, dense, and opaque soup of charged particles. Photons of light were trapped, unable to travel any significant distance before scattering off a free electron. But after recombination, with the electrons now bound into atoms, the universe suddenly became transparent. The photons were finally set free to travel across space unimpeded. These are the very photons that, after a journey of nearly 13.8 billion years, we detect today from every direction in the sky as the CMB. What is remarkable is that the CMB provides a snapshot of the universe before any stars or galaxies had formed. It is a portrait of the cosmos in its infancy, and it is almost perfectly uniform. The temperature variations across the entire sky are incredibly small, measuring only about 1 part in 100,000. This near-perfect smoothness tells us that the early universe was remarkably homogeneous. It had only the most subtle fluctuations in density from place to place. These tiny ripples were the primordial seeds from which all cosmic structure would eventually grow through the relentless pull of gravity. This includes the galaxies and galaxy clusters we see today. But the crucial insight here lies in our ability to map this ancient light. Missions like the Planck satellite have provided us with this information. They have measured the temperature of the CMB across the whole sky with extraordinary precision. This gives us a complete picture of the entire observable universe at that very early time. This stands in stark contrast to our maps of galaxies. These surveys cover only small patches of the sky and are limited to the most luminous objects. In a very real sense, the CMB is one of the few cosmic phenomena we have observed in its entirety. We have a complete map of the sky in microwave light, but it is a map of the universe when it was just 380,000 years old. The universe of today, at 13.8 billion years old, is vastly more intricate and structured. All the galaxies, the great filaments of matter, and the immense voids that define the modern cosmic web have developed out of those tiny fluctuations seen in the CMB. And yet, we have not observed the vast majority of that resulting structure. The invisible universe, in this context, is all the material that grew from those early seeds. It is the structure which we have not yet been able to map. The difference is like seeing a detailed photograph of a field of tiny seedlings, and then trying to imagine the mature, complex forest that will one day stand in its place. We have seen the seedlings with the CMB. The immense task of mapping the forest remains before us. We can explore another aspect of this hidden cosmos by considering a period known as cosmic noon. This was a dynamic era in the universe's history. It spanned a time when the cosmos was between 3 and 6 billion years old. Cosmic noon represents the absolute peak of star formation activity across the universe. Galaxies were creating new stars at rates never seen before or since. If we could somehow journey back to this time, we would witness a cosmos teeming with vibrant, active galaxies. These galaxies would be filled with brilliant young stars, rocked by frequent supernova explosions, and swirling with vast reservoirs of gas. Our own cosmic neighborhood today is a far more tranquil place. Most large galaxies, our Milky Way included, have settled into a slow and steady pace of star formation. They convert just a few solar masses of gas into stars each year. By contrast, during cosmic noon, it was common for galaxies to be forging hundreds, or in some cases even thousands, of solar masses worth of new stars annually. The sky would have appeared brighter, more colourful, and far more energetic. Massive stars, which burn through their fuel rapidly and have short lifespans, would have been much more prevalent. As a consequence, the rate of supernova explosions would have been significantly higher than it is today. Studying this period is essential for understanding the origins of the galaxies we see now. The majority of the stars that make up our own Milky Way were actually born during this earlier, more active phase of its life. To truly comprehend our own cosmic origins, we must understand this period. We need to know what galaxies were like during this peak of creative activity. However, observing galaxies from the era of cosmic noon presents a formidable challenge. Their light has traveled for 7 to 10 billion years to reach us, making them appear incredibly faint. We have created catalogues from dedicated surveys like candles. These used the Hubble Space Telescope to stare deeply at specific, small patches of the sky. But these surveys cover only minuscule areas. Through such efforts, we have observed many thousands of galaxies from cosmic noon. The count may even be in the tens of thousands. Yet, across the entire observable universe, there should be hundreds of billions of galaxies from this period. What becomes clear is that we are only seeing a tiny, biased sample, the very largest and most luminous examples. The more typical, average, and dwarf galaxies from this crucial epoch remain largely invisible. It is these unseen galaxies that hold the secrets we seek. They can tell us about the full range of processes governing star formation and galactic evolution during the universe's most formative years. A particularly intriguing detail is that galaxies from cosmic noon had a very different appearance compared to their modern counterparts. Galaxies in that early epoch of cosmic noon often had an irregular appearance, foregoing the well-defined spiral or elliptical shapes that are common in the universe today. Their structure was noticeably more lumpy, with star birth occurring in concentrated, dense pockets scattered across the galaxy instead of being confined to orderly disks or arms. They also contained a higher proportion of gas relative to their total mass, which is logical given that they were in a period of rapidly converting this gaseous fuel into new stars. A central question in the study of galaxy evolution is how these disorganized and highly active early galaxies matured into the more structured and quiescent systems we now observe. This evolution involves a series of intricate processes, including the consumption of gas, feedback effects from supernovae and black holes, and the merging of entire galaxies. However, a complete picture of these mechanisms cannot be formed without observing extensive samples of galaxies as they progress through this transitional phase. Let's take a closer look at the process of galaxy mergers. Individual galaxies do not live in isolation. They are constantly interacting with one another through gravity, and these interactions can lead to collisions and mergers. When two galaxies combine, their constituent stars, gas, and dust are interwoven over a span of hundreds of millions of years. This event can ignite a period of intense star creation as vast clouds of gas crash into one another and become compressed. It can also channel gas toward the central supermassive black holes, which can, in turn, power quasar activity. A merger has the power to completely reshape a galaxy's structure. For instance, the collision of two spiral galaxies can result in the formation of a single, larger elliptical galaxy. The orderly, rotating motion of the spirals is thrown into disarray by the gravitational turmoil of the merger, which rearranges the star's orbits into a more randomized, spherical shape. When a much smaller galaxy merges with a larger one, it might be entirely shredded by the gravitational forces. Its stars become dispersed throughout the larger galaxy's volume, blending into the host system. Mergers represent a fundamental mechanism for galactic evolution. Galaxies expand by absorbing smaller neighbors, steadily accumulating mass over the course of billions of years. Evidence of such past mergers is inscribed within the very structure of our own Milky Way. We can see long streams of stars in our galactic halo, the vast diffuse region that envelops the main disk. These are the remnants of dwarf galaxies that were consumed by the Milky Way eons ago. These stellar streams are identifiable because their chemical makeup and orbital paths are distinct from those of stars born within the Milky Way, marking them as immigrants from other galactic systems. We can also witness mergers happening in the present. The Antennae galaxies, located approximately 65 million light-years from us, are a pair of spiral galaxies currently in the midst of a collision. Extended tidal tails of stars are being pulled away from the primary site of the impact by gravity. Bright, condensed regions of star formation highlight areas where gas clouds have collided. In several 100 million years, these two galaxies will have fully combined to form a single elliptical galaxy. Another well-known example is the Mice galaxies, situated about 300 million light-years away. Their name comes from the extremely long tails that give them an appearance reminiscent of mice. These tails consist of stars that were ejected during the gravitational encounter. In time, these stars will be drawn back by gravity and integrated into the newly merged galaxy. Closer to our cosmic home, the Andromeda Galaxy is on a direct course for the Milky Way, approaching at a speed of about 110 kilometers per second, or 68 miles per second. In roughly 4 to 5 billion years, our two galaxies will begin to collide. Computer models indicate the merger will be a breathtaking cosmic event, involving several close approaches before the two galaxies ultimately coalesce into one unified elliptical structure. Our solar system is expected to remain intact, though it will likely be cast into a new orbit rather than being destroyed. The night sky as seen from Earth during the merger will be profoundly different, with Andromeda appearing as a vast and brilliant object that would slowly expand over millions of years to fill our view. Detecting mergers at extreme distances, however, presents a significant challenge. The structural disruptions they cause are often subtle and demand high-resolution imaging to be seen. Across distances of billions of light-years, the majority of these mergers are simply not visible to us. We can observe their likely outcomes, such as massive elliptical galaxies that probably formed through mergers, but we cannot witness the early stages of the mergers themselves. This brings us to the role of computer simulations in helping us comprehend the invisible universe. Since direct observation of most galaxies is not possible, astronomers rely on computer models to simulate what this unseen cosmos might look like. These simulations begin with the subtle density variations seen in the cosmic microwave background. They then apply the fundamental laws of gravity, gas dynamics, and star formation to project how these initial fluctuations would evolve over cosmic time. The result is the creation of virtual universes where galaxies can form, merge, and change over billions of years. The most advanced simulations today can follow the paths of billions of individual particles that represent dark matter, gas, and stars. They are capable of reproducing many of the observed characteristics of real galaxies, such as their sizes, morphologies, and spatial distribution. Large-scale projects, including Illustris, Eagle, and TNG, have generated virtual universes of remarkable realism. Examining the output from these simulations reveals a cosmic web of galaxies that closely mirrors what we observe in the actual universe. The simulations correctly predict that the observable universe should contain approximately 2 trillion galaxies, a figure that aligns with observational estimates. They also forecast the existence of populations of dwarf galaxies, low-surface brightness galaxies, and other celestial objects that we have so far only detected in limited numbers. These simulations serve as our most reliable guide to the invisible universe. They provide a framework for what should exist, even if we have not yet developed the means to see it. When a simulation predicts millions of ultra-faint dwarf galaxies, yet we have only managed to identify a few dozen, we can reasonably infer that the remainder are part of this invisible cosmos. They are too dim for our current telescopes to detect, but are just as real in the universe as they are in the models. Of course, the simulations have their own limitations. They are built upon our present-day understanding of physics, which may be incomplete. They also employ approximations and simplifications, as modeling every single detail is computationally impossible. Nevertheless, they are exceptionally powerful instruments for pushing our knowledge beyond the boundaries of direct observation. Looking ahead, future galaxy surveys are poised to shrink the domain of the invisible universe. As previously noted, the Nancy Grace Roman Space Telescope is scheduled for launch in the late 2022. Roman's expansive field of view will permit it to map vast swaths of the sky with great efficiency. Its sensitivity to infrared light will give it the ability to spot faint and distant galaxies. A key part of Roman's mission is the High-Latitude Wide Area Survey, which will scan thousands of square degrees of the sky and observe hundreds of millions of galaxies. This survey represents a significant leap in our ability to map the cosmos. The Roman Space Telescope signals a change in cosmic cartography, moving away from narrow pencil beam surveys to create vast maps of large cosmic volumes. This approach will provide a much more complete sense of universal structure and galaxy populations. On the ground, the Vera C. Reuben Observatory is conducting its own monumental project, the Legacy Survey of Space and Time, or LSST. The Reuben Observatory uses an 8.4-meter telescope, about 28 feet, with an enormous field of view. It is designed to photograph the entire visible sky every few nights, creating a dynamic movie of the ever-changing universe. Over its 10-year mission, the LSST is set to catalogue billions of galaxies, asteroids, supernovae, and other objects. The data it gathers will represent a true treasure trove for astronomers. While LSST will not probe as deeply as the Hubble or Webb telescopes, it will cover a vastly greater area of the sky. This reflects a different strategy that prioritizes breadth over depth, a method highly complementary to deep, focused surveys. Another instrument, the extremely large telescope, is being built in Chile by the European Southern Observatory. It will possess a 39-meter primary mirror, approximately 128 feet across, and is destined to become the largest optical telescope ever constructed. The ELT will have the power to study individual stars within distant galaxies, observe the atmospheres of exoplanets, and probe the early universe in truly unprecedented detail. It will not survey wide areas like Roman or LSST. Instead, its strength lies in providing exquisite detail on specific targets. The ELT will help us understand the galaxies we have already found in much greater depth, characterizing their intricate structures, stellar populations, and chemical compositions. Shifting to another part of the spectrum, the Square Kilometre Array represents the next generation of radio astronomy. Being built in Australia and South Africa, it will be the most sensitive radio telescope ever made. The SKA will survey the heavens at radio wavelengths, with its primary goal being to detect neutral hydrogen gas in galaxies. Hydrogen is the most abundant element in the universe, and it emits a very characteristic radio signal at a wavelength of 21 centimeters, or about 8 inches. By mapping this hydrogen emission, the SKA will trace the distribution of gas within galaxies, allow for the study of galaxy rotation curves, and detect galaxies that contain large amounts of gas but are too faint to see in optical light. The SKA will add an entirely new dimension to our maps of the cosmos, revealing the invisible reservoirs of gas from which future stars are born. All of these powerful new projects will certainly help us, but what is remarkable is that they will not eliminate the invisible universe. Even with all these observatories working together, we will still have observed only a tiny fraction of the estimated 2 trillion galaxies. We might improve our count from 0.0025% to perhaps 1 or 2%. That is certainly progress. Yet, 98 or 99% of galaxies will remain unseen. The fundamental problem we face is the constraint of time. There are only so many hours in a day, so many nights in a year, and so many years in a human lifetime, or in the operational life of a mission. We simply cannot observe everything. This means we are forced to make choices, and every choice to look at one patch of sky means another part of the universe remains invisible to us. It is worth reflecting on the philosophical implications of this invisible universe. What does it mean to live in a cosmos where most of what exists is beyond our capacity to observe? Does the unobserved universe exist in the same way that the observed universe does? Philosophers have debated questions of this nature for centuries. If a tree falls in a forest and no one is there to hear it, does it make a sound? If a galaxy exists but no one ever observes it, is it truly real? From a scientific perspective, the answer to this is a clear and simple yes. The galaxies we have not yet seen are just as real as the ones we have. They are made of the same matter. They are governed by the same laws of physics. The light from these invisible galaxies is traveling through space at this very moment. It exists. It is just that we have not yet been in a position to capture it. There is nothing mystical or uncertain about the nature of the invisible universe. It is invisible only in the sense that we have not yet looked. It is not invisible in the sense of being fundamentally unknowable or existing in some ambiguous state. But there is still something profoundly humbling about this reality. We are finite beings with finite resources, attempting to understand a universe that is effectively infinite. We will never see everything. We will never know everything. There will always be galaxies we have not observed, stars we have not studied, and planets we have not discovered. The invisible universe is a permanent reminder of the limits of human knowledge. No matter how far we advance our technology, and no matter how many telescopes we build, most of the universe will stay unseen. At the same time, an inspiring quality emerges from this fact. The invisible universe is an endless frontier. There is always more to discover. Every single observation holds the potential to reveal something new and surprising. The universe is far more interesting than we ever imagined. Its unobserved portions likely contain wonders we cannot even conceive of yet. This is what keeps science exciting. We are not just filling in the last few details of a nearly complete picture. We are still in the very early stages of mapping the cosmos. The invisible universe ensures that future generations will have just as much to explore as we do. Let us bring this back to the human scale for a moment. Why should any of this matter to you? You are likely not an astronomer. You are not building telescopes or analyzing their data. What difference does it make that we have only observed a tiny fraction of all galaxies? I believe it matters because it has the power to change your perspective. We live in an age where information appears abundant. The internet holds vast libraries of human knowledge. We can find answers to almost any question. With a quick search, it is easy to feel as though we know a lot. It is easy to feel like we have figured most things out. The invisible universe reminds us that we have not even close. The cosmos is vastly larger and more complex than our everyday experience could ever suggest. Most of what exists is beyond our current ability to study. This fact should inspire a sense of wonder and humility. There is wonder at the sheer scale and richness of the cosmos. There is humility in recognizing how little we actually know, despite all our progress. When you look up at the night sky, you are seeing a tiny fraction of what is out there. The invisible universe surrounds you in all directions, vast beyond comprehension. That is something worth thinking about sometimes. This idea also has practical implications for how we think about life in the universe. If we have only observed 0.0025% of galaxies, then we have barely begun our search for signs of life. Every galaxy contains billions of stars. Every star might have planets. The number of potentially habitable worlds in the universe is truly staggering. If life is even moderately common, the universe should be teeming with it. But we have looked at such a tiny fraction of the sky that our failure to find any signs of life so far does not mean very much. The unseen cosmos almost certainly harbors life, and perhaps even intelligent technological civilizations. Our failure to find them so far is simply a consequence of how little of the sky we have actually searched. This reality should fill us with a renewed optimism for the search for extraterrestrial intelligence. We are not running out of potential places to investigate. In fact, we are just beginning. The invisible universe holds trillions of galaxies that we have not yet surveyed. Within each of these, there could be billions of worlds capable of supporting life. When one considers the sheer scale involved, the probability that we are alone seems incredibly small. The fundamental question is not whether life exists elsewhere in the cosmos. Instead, it is a matter of when and how we will finally discover it. To bring these ideas together, let us summarize what has been discussed. The diameter of the observable universe is approximately 93 billion light-years, and it is home to an estimated 2 trillion galaxies. These stellar collections vary dramatically, from dwarf galaxies holding a few million stars to giant ellipticals with several trillion. Every galaxy is a great city of stars, a system bound by gravity that has endured for billions of years. The total number of stars in the observable universe is thought to be around 200 billion trillion, a figure so immense that it defies human comprehension. Yet, we have only managed to observe a minuscule fraction of this cosmic population. As of 2025, the most extensive galaxy surveys have catalogued somewhere between 10 million and 50 million galaxies, each with varying levels of detail. This represents only about 0.0025% of the estimated total. What this means is that for every single galaxy we have seen, there are roughly 40,000 others that remain unobserved. The majority of these hidden galaxies are small, dim, far away, or concealed by intervening dust. They are not invisible in principle, but rather because we have not yet aimed our instruments in the right direction, peered deep enough, or waited long enough. This invisible universe encompasses dwarf galaxies that are too faint for detection at cosmological distances. It includes low-surface brightness galaxies, which are spread so thinly that they fail to stand out against the background sky. It also contains galaxies obscured within the zone of avoidance behind the dust of the Milky Way. There are early galaxies from the cosmic dawn that are too remote and faint for our current technology to see. It includes normal galaxies at cosmic noon that are simply outshone by their brilliant quasar neighbours, as well as merging galaxies whose structural disturbances are too subtle to resolve. The unseen cosmos also holds intracluster stars, which drift in the space between galaxies in massive clusters. It is composed of everything in regions of the sky we have not yet surveyed, and all that lies below the detection thresholds of our telescopes. The invisible universe is, quite simply, the majority of what exists. It is the vast cosmic population that we know must be there, but have not yet witnessed. We are, however, making steady progress. Each year, new telescopes become operational, and new surveys add more galaxies to our catalogues. The James Webb Space Telescope is currently revealing the early universe with an unprecedented level of clarity. The Euclid mission is in the process of mapping billions of galaxies across vast swaths of the sky. Future projects, such as the Roman Space Telescope, the Extremely Large Telescope, and the square kilometer array will push these frontiers even further. Over the next few decades, we will likely move from having observed 0.0025% of galaxies to perhaps 1% or even a few percent. Even with this progress, more than 95% of the universe will still remain invisible. The undertaking is simply too monumental. There are too many galaxies and not nearly enough telescope time to observe all of them. This reality does not mean that we should abandon the effort. Every galaxy we manage to observe deepens our comprehension of the cosmos. Through them, we learn about galaxy formation and evolution, about dark matter and dark energy, and about the history and structure of the universe itself. It is not necessary to observe every galaxy to understand the universe. A carefully selected sample can reveal a great deal, but we must remain humble about the inherent limits of our knowledge. Most of the universe continues to be unexplored. The majority of cosmic history remains unobserved. The invisible universe is immense, and it will stay largely out of sight for the foreseeable future. So, the next time you gaze up at the night sky, remember what you are seeing. You are witnessing a few thousand points of light, a tiny fraction of the 100 billion or more stars that make up our own galaxy. Beyond our galaxy lie 2 trillion other galaxies, each one containing billions of stars. Of those 2 trillion galaxies, we have observed fewer than 50 million in any detail. The rest are invisible, not because they are impossible to see, but because we have not yet looked. They are out there at this very moment, shining in the darkness, waiting for discovery. The invisible universe is all around us, vast beyond our ability to grasp, a constant reminder that the cosmos is far larger and more mysterious than anything we can ever fully know. To appreciate why so much remains unseen, it helps to understand the specific observational hurdles that contribute to the invisible universe. Understanding these technical barriers clarifies why a vast portion of the cosmos remains hidden from view. When astronomers point their instruments toward the sky, they must contend with numerous sources of noise and interference. The pervasive glow of light pollution from our cities brightens the night sky, making faint objects more difficult to perceive. There is atmospheric turbulence, which causes images to blur and diminishes their resolution. The moon, when it is bright, can wash out the light from faint celestial objects. Even dust and gas within our own solar system, which create the faint glow of zodiacal light and scattered sunlight, present a challenge. All of these elements place limits on what our telescopes can detect from the ground. Even when observing from space, high above Earth's atmosphere, challenges persist. Detectors are constantly bombarded by cosmic rays, which are high-energy particles from space. These create false signals in the data that must be carefully filtered out. The instruments themselves are a source of noise. Detectors produce a small signal known as a dark current, even when no light is reaching them. The electronics also generate thermal noise. Every single photon from a distant galaxy that we are trying to detect must be carefully distinguished from all these other sources of noise. For extremely faint objects, the signal might be only marginally stronger than the noise itself. This requires long integration times, where a detector is exposed for many hours or even days to accumulate enough signal to make a reliable detection. This is the reason why deep sky surveys take such an extended period of time. The Hubble Ultra Deep Field, for example, required a total exposure time of more than 11 days, which was spread out over hundreds of separate orbits. During each orbit, Hubble would focus on the same small patch of sky for about an hour before moving on to other observations, only to return later to that same patch. Once hundreds of these individual exposures were combined, the final image revealed galaxies so faint that their light registered as only a few photons above the background noise. This is a painstaking process that cannot be accelerated. It is simply not possible to observe a galaxy that faint in a matter of minutes. To create an image of the distant cosmos is an act of profound patience, a process of gathering light one photon at a time until a picture can finally materialize. Now, imagine extending this effort across the entire celestial sphere. To observe the whole sky with the same depth as the Hubble Ultra Deep Field would necessitate approximately 10 million separate observations. If each of those exposures required 11 days, the total telescope time would amount to more than 100 million days. This translates to an astonishing 300,000 years. It is obviously impossible to dedicate a single observatory to one project for such a duration. Even if we could construct hundreds of Hubble-class telescopes and operate them all in parallel, the task would still take thousands of years. This illustrates a fundamental barrier. Much of the universe remains unseen simply because we do not have the time to observe it all. Beyond the sheer challenge of time, there is the intricate work of identifying what an image contains. When you capture a deep exposure of the sky, you might record thousands or even tens of thousands of faint objects within a single frame. While most of these are galaxies, some are individual stars within our own galaxy. Others could be asteroids orbiting within our solar system. Still others might be mere image artifacts or electronic noise. A crucial step is to differentiate among these various sources. Galaxies typically manifest as extended, fuzzy shapes, while stars appear as distinct points of light. A complication arises with very distant galaxies, which can also look like point sources, because they are too far away for us to resolve their structure. Identifying asteroids requires multiple observations made at different intervals to track their motion against the stationary backdrop of stars and galaxies. Furthermore, confirming that an object is indeed a remote galaxy and not a nearby star that happens to share the colors of a high redshift object requires the use of spectroscopy. Every part of this process demands significant time and effort. For each object detected in a deep image, hours of subsequent analysis may be needed to classify it correctly. Even with the aid of automated algorithms and machine learning, there are limits to how quickly this work can be done. The invisible universe, therefore, is composed not only of objects we have yet to photograph, but also of objects we have photographed, but have not yet properly identified or categorized. It is likely that millions of galaxies are currently sitting within existing telescope data archives, unexamined because there are simply not enough astronomers to process all the information. Another critical concept to consider is how selection effects introduce bias into our view of the universe. Every astronomical survey is subject to these effects, which are systematic biases that make some types of objects easier to find than others. Bright objects are more readily detected than faint ones, so surveys are inherently biased toward luminous galaxies. Large objects are easier to resolve than small ones, which means surveys are also biased toward massive galaxies. Objects with particular colors tend to stand out more than others, creating color-based biases. Moreover, certain regions of the sky might be observed preferentially, either because they are well positioned for specific observatories or because they happen to be in fields that were targeted for other research. What all these selection effects mean is that the galaxies we have observed do not constitute a representative sample of all galaxies in existence. They are, instead, a biased sample, skewed toward the bright, large, colorful galaxies that reside in well-studied parts of the sky. When we attempt to understand the properties of galaxy populations from our observations, we must account for these inherent biases. We have to ask what portion of the total population we are actually seeing. For certain kinds of galaxies, like giant, bright ellipticals, we might be observing a large fraction, perhaps 50% or more of those that exist in the surveyed areas. For other types, such as ultra-faint dwarf galaxies or low-surface brightness galaxies, we might be seeing less than 1%. The invisible universe is disproportionately composed of the very types of galaxies our surveys are not well equipped to find. Astronomers work to correct for these selection effects by using statistical methods. They create a model of a survey's selection function, which describes the probability of detecting an object as a function of its properties. Using this model, they can then estimate the total population by calculating what the survey would have missed. This is precisely how we arrive at figures like the estimated 2 trillion galaxies in the universe, even though we have only directly observed around 50 million. The estimate is built upon observations of the galaxies we can see, combined with statistical corrections for the galaxies we know we are missing. However, these statistical corrections carry their own uncertainties. The true number of galaxies could be closer to 1.5 trillion, or it might be as high as 3 trillion. We will not know for certain until we can observe a much larger fraction of the cosmos. Now let us consider the timescales involved in cosmic evolution and how they connect to the invisible universe. Galaxies evolve on incredibly long timelines. A typical galaxy might take hundreds of millions of years to form as it gradually accumulates gas and dark matter, ignites star formation, and grows in mass. Once formed, its evolution continues over billions of years. Sometimes it forms stars at a steady rate, while at other times it experiences intense bursts of star formation triggered by mergers or inflows of gas. In other cases, a galaxy can become quiescent, with very little new star formation occurring. These are vast stretches of time, far longer than a human lifespan, and far longer than the entirety of human civilization. We are unable to watch a single galaxy evolve in real time. We can only capture snapshots. But by observing a great number of galaxies at various distances, which correspond to different points in cosmic history, we can piece together an evolutionary sequence. We can see what galaxies looked like 1 billion years after the Big Bang by studying objects so distant their light has traveled for 12.8 billion years to reach us. We can see their appearance at 5 billion years by looking at galaxies at intermediate distances, and we can see what they look like today, 8 billion years after the beginning, by observing galaxies in our local cosmic neighborhood. By combining all these snapshots, we construct a picture of how galaxies change over cosmic time. This method, however, only works if we have substantial samples of galaxies at all the different distances. Gaps in our observations create corresponding gaps in our understanding of this evolution. The invisible universe is the source of these gaps. There are epochs in cosmic history from which we have relatively few observations of galaxies, either because galaxies at those particular redshifts are especially difficult to detect, or because surveys have not concentrated on those distances. These gaps leave significant uncertainties in our evolutionary models. For instance, we might see that galaxies at redshift 2 have a certain appearance, and galaxies at redshift 0.5 look quite different. But without observations at the redshifts in between, we do not know precisely how or when that transition took place. In this way, the invisible universe obscures the intricate details of cosmic evolution. There is one more aspect of this invisible universe that is particularly fascinating. It is entirely possible that the cosmos holds structures and phenomena completely beyond our current understanding, hidden from us simply because our view of it remains so limited. The history of astronomy reveals a consistent pattern. Each time we have extended our senses into new observational frontiers, we have been met with the unexpected, whether by looking in new wavelengths of light, achieving sharper resolution, or peering across greater cosmic distances. The discovery of quasars was an unforeseen revelation, as were the enigmatic flashes of gamma-ray bursts. The existence of dark matter and the accelerating expansion driven by dark energy both emerged as profound surprises. Even the grand, web-like arrangement of galaxies, known as the cosmic web, was a structure that had not been anticipated. Every one of these breakthroughs depended on observations that reached beyond the limits of what was previously achievable, which makes one wonder what other surprises might be waiting in the invisible universe. The answer, of course, is that we do not know. That is the very nature of a surprise. Still, it is reasonable to expect that once we finally observe a meaningful portion of the estimated 2 trillion galaxies, we will encounter phenomena we could not have predicted. Perhaps there are entire classes of galaxies with properties unlike any we have ever catalogued. It is conceivable that structures exist on scales far larger than we currently believe is possible. There may even be populations of cosmic objects that we have not yet begun to imagine. The unseen universe is a vast reservoir of potential discoveries, and we can only learn what it contains by actually looking. This is precisely why it is so crucial to continue pushing the boundaries of observation, even when there isn't a specific hypothesis to verify. Exploratory surveys, which are designed to map enormous volumes of the universe without focusing on pre-selected targets, have often led to the most astonishing findings. The Sloan Digital Sky Survey, for instance, was not conceived to locate any single type of object. Its purpose was to systematically chart the sky and document what was there. In doing so, it discovered quasars at higher redshifts than had ever been seen before. It mapped the intricate structure of the cosmic web with new detail, and it identified unusual galaxies that did not fit into existing classifications. These revelations were a direct result of simply looking, of a dedicated effort to make the invisible universe visible. This same principle of discovery will undoubtedly apply in the future. When the Roman Space Telescope conducts its survey of billions of galaxies, it is almost certain to find unexpected things. When the extremely large telescope examines distant galaxies with unprecedented clarity, it will surely reveal phenomena we have never witnessed before. The invisible universe is not merely a scaled-up version of what we already know. It contains true unknowns, and it is the pursuit of these unknowns that propels science forward. So, what insights can we take away from our exploration tonight? We have considered that the observable universe likely contains around 2 trillion galaxies, yet we have studied only a minuscule fraction of them in any detail. We have touched upon the different kinds of objects that populate the invisible universe, from dwarf galaxies and low-surface brightness galaxies to distant primordial galaxies and wandering intergalactic stars. We have acknowledged the immense challenges of observation, including the time and resources needed to detect such faint and faraway objects. We have also seen how selection effects can create a biased perspective of the cosmos, and we have reflected on both the philosophical and practical consequences of residing in a universe where the vast majority of what exists is still beyond our sight. The scale of the invisible universe is far greater than that of the observed one. For each galaxy we have carefully examined, tens of thousands more await even a first glance. For every star we have catalogued, trillions more remain uncounted. For each planet we have detected, countless others are waiting to be found. This realization should instill in us a profound sense of wonder and humility, wonder at the sheer richness and scale of the cosmos, and humility regarding the limits of our knowledge, even with all our technological advancements. But this feeling should also serve as an inspiration to continue exploring. The invisible universe is not permanently beyond our reach. It is simply unseen for now. With more advanced telescopes, more dedicated observing time, refined analysis techniques, and our continued commitment, we can render more of it visible. We will likely never see all of it, as that seems an impossible task given the constraints of time and resources. We can, however, always see more. We can continue to push the boundaries ever further. We can unveil new corners of the cosmos and discover new wonders within them. That endeavor is worthwhile, not only for the scientific knowledge it yields, but also for the broader perspective it offers us about our own place in the universe. Thank you for joining me on this journey through the invisible universe. If you found this exploration to be of value, your engagement helps ensure these deep dives into the cosmos can continue. Always remember that the universe is immensely larger than what we can perceive. Every time we look deeper, we find something new, and that is its inherent beauty. The invisible universe is not an empty void. It is filled with wonders yet to be discovered. It is full of galaxies waiting to be catalogued, stars waiting to be studied, and perhaps even civilizations waiting to be contacted. The frontier of cosmic exploration stretches endlessly before us. We are surrounded by mysteries, and that makes this a most exciting time to be alive and to be looking up at the stars. Good night, and may you never see the night sky in the same way again.